Hey guys, this is me Aviraldwivedi Vedi and you are listening on Extended Reality Developers of India community. Today we are going to do this a bit technical session with Videep Mishraa. Videep Mishraa is a great engineer of graphics. So he's going to teach you a lot of things about computer graphics today. He is going to dive deep into rendering pipeline and give you a glimpse of how computer rendering works. So without any further delay, Videep is a very great friend of mine and he is with us today. He's giving us his time. So let's welcome him on the screen. So hi Videep, how are you?
Thank you so much, Avi. I'm fine. How are you?
I'm really good. It's a pleasure to host you on our Discord server today, and we are really delighted to have you on here.
Thank you so much. Actually, I'm honored to be here to share some knowledge that I have a little bit with you all. It's great to be here.
Yeah. So Videep also has his own channel. So make sure you follow his channel as well on YouTube. He is doing some great stuff. He did basically about almost the same session on his channel as well, where he mentioned a lot of things about rendering pipeline. And today we are expecting the similar session. And rendering pipeline, I would love to give you an introduction. So for example, whatever you see on your screen when you play a great game, whenever whatever the kind of game it is, whether it's 2D, whether it's 3D, it's done by some sort of rendering pipeline. The process is called rendering, and the idea is to generate 2D images from a bunch of code. So Videep is going to guide you what that code is exactly doing in between those, what sort of algorithms are used. So Videep, yeah, stage is yours.
Thank you so much, Avi. Thank you so much. All right. So first of all, good evening, everyone, and I hope you're able to see my screen here. So as Avi said, yeah, I'm a Unity developer, a bit of a programmer, yeah, and you can see this introduction screen has my YouTube, LinkedIn, and Twitter account. So if you just want to get in touch with me anytime or you have questions, suggestions, I'm definitely open to them. So just a quick glimpse on what we are going to quickly be able to achieve by the end of the class is very simple. You might have been seeing this floating around over the internet somewhere, maybe not, but some kind of an effect which is so simple to create that you don't even need animation for that, or a rigged animation for that. You will be able to code this. Okay. Without wasting any time, let's get into this on the slides. So key takeaways here are going to be the basics of graphics pipeline. Okay, we'll discuss what graphics pipeline is. Basics of CG. CG is C for graphics, which enables us to write shader code, which can be then compiled onto DirectX or OpenGL, either runtime, or it can, you can compile it and then run it on. Then we'll learn this shader lab syntax. So what happens is when you write some shader in Unity, you need to follow the shader lab syntax so that Unity understands that this is a shader. All right. Types of shaders, we'll just run over through them because 1 hour is very less to go through them. But yeah, we will have a series if possible. If you suggest, it's all up to you. We can do a series and we can discuss shaders at length. Then today's topic is going to be vertex and fragment shader that you can code. And of course, you're going to write your own first shader today. At the end of the workshop, I am really believing and hoping that you will be able to pull up shader code and go through it and understand it. Right now, sometimes what happens is you open up a shader code, but it's not readable or understandable. But after this workshop, I'm really hoping that you can do it. And if you are, message to us. All right. Couple of assumptions here that I would like to make that you might be knowing is what pixels are and how displays work. Don't mind, I won't be opening up the LCD here, but it will be great to know how simple display works, because eventually when you connect your display to the hardware, that is what you're going to render on, right? You're going to provide the output of the display, and it is what everybody needs or requires to play a game, to watch animations. Of course, it will be great if you can write code, but very basic code, variables, arrays, defining functions, that's all. Mathematics also basic. I mean, so honestly, I'll tell you, we won't dive into the dot products or vector mathematics, matrices, calculus, determinants, etc. Not an issue. It's just simple how to plot points, how to draw lines, triangles, circles, octagons, hexagon, all those things, right? Uh, if you understand gaming and animation, that's great. That's great because you might be knowing like how frames render, uh, how what is the specific frame rate that we need. Uh, it now after this, if you do understand what a painter's algorithm is, it's perfectly fine. And if you don't, it's perfectly fine because in simple terms, what we're going to do is just like a person draws or creates paintings, we are going to similarly apply same kind of logic here, and we're going to see same kind of things here, where you paint a base layer, then you add some more objects to it, then you paint that, then it's basically layer wise painting. So just to give you a small example, you paint the sky, then you paint some mountains, then you paint a house, then some trees, and then, you combine those layers. So basically you have a canvas and you start painting. This might be sounding obsolete because of the z buffers, and z buffers store a lot of data, which is the depth of the specific pixel. If you do understand that, that's great, but while we do this session, you will have a basic understanding of that as well. And then the game loop. All right, so the game loop, perfectly fine if you understand that, perfectly fine if you don't. A game loop is basically, when you're running a game, until and unless the user asks or stops it, okay, there will be a certain number of functions that will be called. After a function is executed, whatever time it takes, you'll then again call the function again, so that they can call their own specific functions. And this is very much seen in Unity. So if you are familiar with Unity, it will be great, to be very honest, because when we talk about Shader Lab, we are going to talk about Unity. And let's quickly get started with some basic simple stuff. Now, when I said that you need to know a bit of mathematics, right? As base, what I would really expect you to know is points, lines, triangles. Forget about patches for now. All right. So if you might have coded on or programmed on OpenGL, it's perfectly fine. But if not, see, whenever like when I was really young, right, I used to paint on the walls, and I used to paint on every possible thing that I had with a pencil or a crayon. But then how I learned to draw is basically when my mentors told me that, okay, join the dots, simple. So you have dots, you join them, you create a line, uh, and two dots. If you have two dots, you can create a line. If you have three dots, you can go and create a line on those three dots, connecting so that they are triangles. And then you can make squares, rectangles, hexagons, octagons, whatever you want. And then you must have seen those books where you join the dots and a scene is created. That is what we are going to do. All right. The idea is to plot certain amount of points in 3D space and connect them. It's as simple as that. Okay. So when we talk about graphics and we are rendering and we are making 3D and all, what are we doing is basically we are looking forward to plot certain points in 3D space. OpenGL, you might have heard about GL point, GL line, triangle. Then if you say you can go in depth with line strips, triangle strips, and all those things, but forget about that right now. I just want you to understand very simple stuff. You have point. The size of a point is of approximately, not approximately, but 1 pixel. Okay. You start off by, I think I'm getting some noise here.
So, so
Yeah.
if you are not speaking, please mute yourself because that will create echo otherwise.
Right. Thank you. So, right. And then when you join the points, if you draw, if you ask GL, OpenGL to draw a line, you can have a line. But let's talk about two major primitives that are going to enable you to modify the existing graphics pipeline. The first one being the point, okay, where you plot whatever number of points are there in 3D space. And the second one being the triangle. So now what I'm going to do is I'm quickly going to open up 3D Studio Max. Okay. Why 3D Studio Max is because I want to go away from the traditional gaming softwares and show you 3D softwares, 3D software which utilizes the same concept. So if you see this 3D Studio Max that I use for basically creating 3D artwork, you can see that it already has vertices. You can click and you can move around. You can just move around the vertex. Okay, like this. You have edges. So these are the lines that are connecting these dots. 3, right? And then you have the face. The face is basically, when you say that this is a triangle and color it all up. So you have got a face. Now, why do we need 3 points? Is because if you want to ever form a plane, the minimum requirement would be 3 points so that you can, have a visible plane. All right. That is quite it. And now if you see, you have a gizmo and you have a center point of that specific triangle. So what I'm going to do is I'm going to quickly open up Unity, and oh, it opened up on the other screen. All right. So transformations, here we go. Yep. Now we have a scene in Unity, and I hope you must be very familiar with this kind of UI. Unity, if you must have been using, you would definitely be familiar with that. What I've done is I've got the triangle from 3D Studio Max and exported it into Unity. The format is FBX. You can use OPG as well, up to you. But the reason for doing this is very straightforward and simple. We need to first understand how the data that we are going to modify is passed on from the CPU to the GPU, and how do we get access to that data, right? So in 3D, basically in Unity, if you just go and create any object, okay, you can just go here, create a 3D object, and if I create, let's say, a simple cylinder, right? For now, you would see it has got a couple of components here. So guys, if you have gone in depth with those components, it's really great. But if you have not, then just you can just drop in a comment that okay, you have not gone through that. But we are going to go through that, right? So you create a 3D object and you can just move it around, and you can perform whatever 3D operations on it in world space. And similarly, why I'm going to use a triangle is because let's talk about the basics. Okay, I want to talk about the basics here. So we have a triangle here, okay, and let's check out the components. Now the components are transformed, so it has the the original like position, rotation, scale, and that is quite it. So you must have definitely used that, right? And it's very straightforward to understand what that is. Second thing is that we have the mesh filter. Now here is where things start getting interesting. Why? Is because the mesh filter consists of a mesh, right? If you must have noticed in the 3D Studio Max window, what I had was an editable mesh, right? If you see here, it's an editable mesh. So mesh is basically a class that contains the data that is required for us to draw this kind of a geometry on your screen, okay? Which means that if I am just going to say that don't provide it a mesh, right? I'm not going to render anything. Now this is the game window. This helps us visualize what we are going to render and we are going to see on our display screen or an output screen. So if I say that I don't have any mesh, sorry, don't render. Uh, GPU is going to say, all right, go ahead, no mesh, I'm fine. But then what is this mesh all about? As we understood earlier, we had points, all right? Now these points are called vertices, and we have triangles, all right? So if we have a quick look at what Unity says, the mesh and will have certain triangles, so not basically certain points, vertices. The vertices will be assigned to some indices. These indices are basically going to help us draw the triangle. Let's take a look how this is done. So right here, if you see in this specific script, right, I have made a component saying vertex information. In that, I'm accessing the mesh filter. I'm getting the mesh out of the mesh filter. Now this mesh specifically has a lot of properties. So it has a lot of properties, right? For now, we should not be concerned about many, but some, which are the vertices, and we'll get about the indices later on. All right. So if you see, if I just switch on the script, what's going to happen is I'm going to take some data out of that mesh. So even if you get this data from 3D Studio Max, or even if you run the script on a cube, I'm just going to run the script on a cube or a quad, I'm going to show you the same data. The data has been successfully transferred from max with 3 vertices. All right, so if I expand this, the first 3 are vertices, the next 3 are the indices for the specific vertex, and hence we get to know that the vertex position at index 0 is 0.50. So if you see, if I just was to create a new sphere with 0.5 and 0, you see the center of this has been mapped to this vertex. All right. Similarly, the second one, if we just map it, to 0, minus, zero point 0.5, it's 0.5, 0.5, minus 0.5, and there you go. That's the second. And the third vertex, this is the third vertex. All right. Now, what happens is we got the information for the vertices, and we have mapped them to the indices. Why we do usually map the vertices to the indices? Just the basic thing is like, we just want to refer to the indices always when we are creating a triangle. So if you see 0 1 2 is the first triangle, so 0 1 and 2, this is the first triangle, and with this triangle we are using these vertices to render out. So that's great. Now when we already know that we have this triangle, we understand the importance of this mesh filter as it contains the mesh. But then what about this mesh renderer? Why do we need that? So we need the renderer because the renderer will contain.
Hello,
Hello?
sorry for interrupt, but are you sharing the screen?
Yeah, I am sharing the screen. Is it visible,
No,
guys?
it's not visible. It's not visible.
Oh,
For me, it's visible. For me, it's visible. Don't worry. Make sure you click on Videep's name and click on Watch Stream. Okay, so there should be a Watch Stream button on Videep's name. So hover on Videep's name and you'll see a Watch Stream button. So it's visible. You'll
Oh,
have to
okay,
click on
okay,
that.
okay.
Yeah. Please continue, Videep.
okay, awesome. All right, so we will dive into the mesh renderer. Now, the only thing that I want you to take away from the mesh renderer right now is the materials. Okay, so if we check the mesh renderer, we are taking this data from the mesh and we are asking, it to map it to the specific material. And if we say don't have any material, the GPU is like smart. It's like, okay, there's no shader program that I have to attach it to. So it's not supposed to be rendered. This is a display. And it's so simple. You can get any kind of mesh from anywhere. And 3D Max, Maya, whatever you can, use the primitives in Unity. And it should have a mesh filter with a mesh and a material, and it's all rendered. Then let's check out the material. So what is a material here? The material, in a very simple term, is an interface which has a shader. Okay. So the material is an interface for artists so that they can quickly tweak these properties. All right. Whatever properties they want, they can add some map or whatever we want to do. For developers, we can say that mesh has the material has couple of properties that we can access. Like at runtime, we can set these maps, we can change the colors, etc., etc. For graphic programmers or developers also, graphic developers, programmers, whatever you want to call them, the material will consist of a shader file. That shader file is responsible to modify the data in the graphics pipeline. Okay, so that is the basic. So you have a mesh, you have to attach a material to the mesh. The material is an interface to the shader. Very simple. Now I want you to quickly answer one question here, that if I am using this transform, right? So I'm just going to put the script off. If I'm going to transform this, let's say 1 unit in X, right? We saw that we had the vertices 0.5 and 0 for the first vertex. That was the position. Will it change? It should change, right? I mean, why will it not change? It should change. But no, it does not change. The reason being, the vertex information saved in that specific mesh filter, in the specific mesh, right, is with reference to the pivot of this object. So guys, this is very important. The very first and the basic step in graphics pipeline that we need to understand is the object space, all right, the local space. So whenever we are talking about the vertices with reference to its pivot, the specific object, right, we are talking about the object space. That means wherever I move, okay, wherever I just take this triangle, how much wherever, okay, I'm going to clear it out, read on the script. The vertices are going to have the same position in the mesh, okay, but they will have different position in the world. So the camera will not render it. All right, you see that? And this is magic, but it's straightforward mathematics. How? Let me quickly share. This is one triangle that we have, all right, and we are talking about the vertex space. I made another triangle in 3D Studio Max right here. And what is the difference between these two? If you check in Max, all right, you can see the pivot point to the bottom. This triangle has a pivot point to the bottom, whereas this triangle has the pivot point to the center. Now, when we go to Unity, and I'm going to switch this on, right? Did you see this? The first vertex, the very first vertex is 0, 1, 0. So the Y position for the very first vertex has gone to 1. Now we understand that whenever we are, getting any mesh inside this mesh filter, we are always going to talk about the vertices with respect to its pivot point. Okay, and that's why let's talk about this triangle quickly and also understand one more thing. How do we represent that position in terms of colors? So as position XYZ is has three values X, Y, and Z, and a color is also comprised of three values RGB. What we have to do, we can do is we can simply write a quick shader saying that this vertex will have specific color, vertex 1, this vertex will have a specific color, and the third vertex will have a specific color. I already have that material right here, and I think so this, no. Yeah, so if you see, this is a very good representation where you see the first vertex has x0 green, which is x if we map it to r red is 0, y is green, which is y is 1, so you have green color, and z of course blue, it is 0 again. This vertex is black because 0 0 0 xyz rgb 0 0 0, and third vertex, this one basically is x is 0.5, which is basically half of red, y is minus 0.5, I guess. Yeah, y is for this one, let me check here. Yeah, so this one is yeah, x is 0.5, y is minus 0.5, and z is 0. So you have that red color. So this is very simple. Like if you now have to understand, and if we have to render any object to by assigning colors to it, you can definitely do that. Okay, we will take a look at how this is done. So the first thing that we know and which is clear is object space. All right, and let me quickly go towards this slide. So we know we have discussed about the points that form a triangle, the pivot, which is very important, which defines the position of the vertex of that specific object. Mesh filter, mesh render, vertex position in terms of the object space. And then when we have this object space, position or transformation multiplied by the transform component, we get the world space. Now, what is world space? Simply put, to represent this triangle with respect to a 3D world, all right? If I have to see this 3D world, I'm just going to create a 3D cube, and I'm going to put it at 0 0 0. This is the origin of this 3D world. If I put in wireframe right there, the position of this triangle with reference to this 3D world is going to take and understand, is going to give us the world space coordinates. All right. The process of taking these vertices which are present in the object space to the world space, all right, and then being viewed by the camera and then being projected on the screen is called the graphics pipeline. You know, the programmers have defined a custom pipeline saying that, okay, this is a way that it should be done. And that pipeline, we are going to just see it now. If I switch on the gizmo and show you the camera, there are three things to consider. We have already taken a look at what is object space vertices, what is the value of object space vertices. Once we multiply this, a simple matrix multiplication that you can do using mathematics or some libraries, you get the world space position. So if I'm going to just move it here, the vertex is going to be this vertex position multiplied by this transform component, and you will get the world position. Now, once you get the world position, you have to see it from the camera's perspective, because if you do not have a camera, right, then you are not rendering anything. So there should be a specific camera as a tool which defines, okay, this is a frustum, right? There is a, you see the trapezium right here. This is a frustum and I want to see things in this frustum only. So that is just a tool for the programmers to, say that, okay, there are certain objects and whatever is inside this volume, just show that to us, which means this, if you see this box, all right, and you see this camera, we are calculating the points of this specific volume or an object, converting that from object to world space. From world space, we are calculating where exactly is it in, the camera. So if I just move the camera like this, see the triangle has been hidden now, and the cube appears to be moving here. It's not the cube that is moving there. All right. The camera has moved, but the transformations of the camera has been applied. Hence, the cube has been moved. So camera is just, you can just say a set of matrices, a set of transformations that have to be inversely applied. Now, why inversely applied is because if you see from the camera's point of view, if the camera is moving towards the right, the objects are moving towards the left, right? Agreed? If the camera is moving towards the left, objects are moving towards the right. Similarly, with all these axes and the transformations, rotations also, all right? So this is a specific matrix or set of numbers that we inversely multiply with the object, because we only have these vertices that we have to display. All right. I hope a bit of this is clear. If not, yeah, we will discuss it at the end. But the idea is, I'm again repeating here because the more we iterate over this, the more clear it's going to get. The idea is, the first thing that we have to consider is that object's vertex location with respect to its pivot. Get that vertex location with respect to the world, right? This is the world, and the world's origin or 0, 0, 0 is right here somewhere. Let me check. Right here. And then we need to calculate the same vertices, the same transformations for the vertices, same vertices with respect to this camera. But the game does not stop here, because if we just do the calculations and do not project it on the screen, then we will not get this kind of a result, which means this won't be 3D or it won't even appear, right? So what we have to do is, once we convert the vertex information from object to world space to view space, right? We have to project it on the screen, and for that we need a trapezium. This is called a frustum, which has a near plane. Now the important thing is, this is a near plane. If I, see how it is clipping. Now you understand why it is clipping, because this object is out of the frustum. Simple. Similarly, it has a far plane, and then it has a field of view. Okay, so you can form your projection matrix, multiply that with the vertex position, which is already in the view space or the camera space, and then the output that you get has to be mapped onto the screen. Okay, interesting part is, I cannot provide this near clip as 0. I don't know if you must have tried this or not, but you cannot do that because the projection has to be done on a screen, and that screen cannot converge at 0. It's very simple. It's very simple. So that said, let me quickly go to the slide. Once we do the vertex position convergence, okay, we see this is the same thing that we explained, right? We have the coordinate system, or the information about the vertices with respect to the object, and it's called the object space. If it's in relation to this world, it's called the world space. And if assume there is a camera here, right? If the position of any of the vertices of that object with reference to the eye space, it's called the camera space. Next is the projection transformations. Okay, this is the model view or object space to world space, then world space to view space, camera space. Right? Then you have the projection transformation. So if you see, this is exactly what's happening. The viewer, or we are viewing this because this is being rendered on this on this plane. So everything gets projected, like projected onto this plane. Okay. So good amount of mathematics. You have culling going on here, you have culling going on here. This is the frustum that we just saw. And that is called the graphics pipeline. So whenever you want to open up or create your own application using OpenGL or DirectX, this is the very basic thing. You get the vertices, you transform them, modify them, and show it on the screen. If your application has a support for these things to be modified by another user, right? Then the pipeline that you write is going to be programmable, right? Now let's say I create an OpenGL application in which I just give that, okay, I'm going to have a form shader, I'm going to have a blend shader, I'm going to have a standard shader, and I'm going to have an unlit shader. And I give those things to the user. So the user is going to say, yeah, this functionality is just here, but I want to still modify and program this functionality to make things look better, right? That is where, I would take help of either exposing some APIs or some integrating some compilers, which will allow other users to write their own code. All right. That other code is going to be modifying the data that is being processed on the GPU. Here it is very important for us to understand the difference between the CPU and GPU in a very simple way, that why we prefer these calculations on GPU is because these are interdependent. Okay, sorry, independent. These are independent. So if I am rendering this triangle, for example, all right, I can render or calculate, the position of this vertex on the GPU by multiplying those matrices that I earlier mentioned. And on this next thread, parallel thread, I can do the same for this vertex and this vertex. Okay, so it becomes very fast if you're doing these things on GPU. If you render, like you must have seen 3D Studio Max rendering and all, right, or Maya and all. So they have CPU renders, right? When you're rendering on the CPU, it's a different story altogether. And then you can do ray tracing and all, which you have your own custom algorithms that you apply, and it's done, right? So you have GI calculations, this and that, ray tracing, then caustics, and all those things. But here, keeping it very simple, we are using the power of GPU at runtime to parallelly process all this data. That said, let's talk about the graphics pipeline. When you are using the power of GPU to render out certain, or calculate certain geometry, then render it out and provide an output to the hardware, right? This set of specific instructions or flows or functions in a certain manner is the graphics pipeline. And as you see, it is very well mentioned that it's a conceptual pipeline. That means there is a concept behind it, and we are following that concept where you have an application. The data goes from the CPU to the GPU and is stored in the VRAM, video RAM, right? GPU talks to the video RAM, and then quickly does its calculations, matrix multiplications, whatnot. And The rasterizer then is responsible to paint the pixels and show it on your display screen. Like whatever is here has been done by the same. And it's not necessarily exactly like, you know, you have to use OpenGL DirectX. There is Windows GDI Plus also for rendering, what do you say, graphics, because it's graphics device interface. Windows has its own graphics device interface, right? But let's talk about OpenGL and DirectX here, as that is more, what do you say, gives us more power, right? So, divided by plus, yeah. Now the pipeline. When we saw that we were processing all this data, where do we get to know what goes to the GPU? Whatever is being rendered with the help of a shader is going to the GPU, right? And whenever I create my OpenGL app and I don't allow the other user to modify it, I'm defining a fixed function pipeline. That means these functions are already defined in my application. But if I'm exposing the APIs to you or any other developer to modify them using a shader at runtime or a compiled shader, pre-compiled shader, that is, that is what I'm giving you an option to program the pipeline. So it becomes a programmable function pipeline because you're programming the function. Which means if we go to the basic pipeline, it says you have an application which calculates the, vertices. So you have the matrix calculations done in terms of, there are certain number of vertices in the specific object. You have the object space, uh, vertex position, and then what is the matrix that it has to multiply by to get the world space, what is the matrix that it has to multiply by to get the view space, and what is the matrix that it has to multiply by the projections, by the project for the projection, basically, to get the clip space. All right, which means we have vertices. This phase between vertex program and the geometry program, okay, is called a primitive assembly, where you assemble the primitives, which are the primitives is like triangles and all. Mostly for now, just understand triangles. Okay. OpenGL and DirectX, they have been allowing the tessellation shader. So when you go through this pipeline, consider vertex program as a vertex shader, geometry program as a geometry shader. Then the clipping and the rasterization happens, right? Where whatever data is not necessary is being clipped off and discarded. Then you have a fragment program. Here, basically, you decide. Um, I'll show you. Why is this triangle, right? Um, why is this triangle not just showing one pixel of green color, one pixel of black color, and one pixel of red color? Because we're calculating the derivative and we are sampling from one vertex to another vertex, right? So the fragment will basically, there is one saying, I'll tell that. A pixel, okay, a pixel can have multiple fragments, but a fragment will always have one pixel to render, all right? And then it is the rasterizer's job to basically rasterize this data, because we are telling the GPU that, hey GPU, I want a triangle to be drawn. These are the three colors at these places. Now you interpolate. Okay, now you interpolate. So the rasterizer will interpolate the area between this basically triangle. And if you zoom in at a pixel level, it will calculate what all pixel lie in this specific area. And if you see here, if I'm just going to, just put off these spheres so that you understand. It starts with exactly one pixel. I'm sure you're not able to see it. Starts with exactly one pixel where green is 0.5. Interpolates towards red where red is 0.5. And where black is full, so 0, 0, 0. This is the job of the rasterizer, where, for this object there will be a fragment shader that will be running and calculating the value for this specific pixel right here. That's said and done. Let's go over this pipeline. So we say that we have an application, we have a vertex program, which is a vertex shader. The role of that vertex shader is, it will go to the GPU, say that, okay, I have a data structure here, all right. I have to multiply the object space position of that vertex and provide an output in clip space, all right. That means I'm going to provide an output by doing all the mathematical calculations that you require on the GPU on multiple threads. Then you have a tessellation shader where you basically, add more geometry, but let's not talk about it right now. You have a geometry program. Also in geometry program, you can create geometry and triangles or, whatever specific geometry at runtime. Let's not talk about it right now. Clipping and rasterization, of course, whatever is not inside the camera's frustum, clip it off. Okay. Then the rasterizer invokes the fragment shader, which says that, okay, I have got this specific area, I have to color this specific pixels, and I have the information of a texture or a color, right? That information. Here we also, can say that whenever we are rendering objects in a specific way, or when they are arranged in a specific queue, right? For example, let's say you have a triangle which is an opaque geometry, right? Then you decide, no, I want to add a glass on top of that, right? So you take that fragment, you process that object, then you say, no, I want to have a fog also on top of that. So basically, one pixel has three fragments. First, being responsible to shade the object which is opaque. Second, being responsible to shade the object being transparent, that may be translucent or might have reflections. Third, being the fog. That said, you are already rendering 3 fragments per pixel right here. Okay. And if you want to understand, I have given a gray color as a background, so the buffer is already going to have gray color by default. That means you can relate to the painter's algorithm where you are actually painting a layer by layer, right? So you go paint layer by layer and get your final output. Okay. And then you can do your hidden surface removal kind of things in the frame buffer operations. But right now, what is most important to start off with shaders is how do you modify the data in the vertex program, and how do you modify the data in the fragment program. Understanding that vertex is required to change the position of this model, right? If I now you tell me, if I change the data in the vertex program, right, I have got 3 transformational matrices. I can change the model in the object space itself, I can change the model in the world space, and I can change the model in the clip space. All right. So that said, if I want to change how the model looks, the vertices look, right, I can do it in the vertex program. But in the same place, if I want to change how the model uh, rasterizes in terms of the shades, in terms of the lighting, in terms of the shading, in terms of the transparency, in terms of clipping, in terms of um, alpha cut, basically you want to have a transparent texture, I can do that. I can say in the fragment shader that, okay, this pixel has an alpha value of 0, that means discard this pixel, I don't want this pixel to render. As simple as that. You get the transparency, whatever is in the background, if the skybox is in the background, you get a skybox. So this is some information on the pipeline, because this is a big topic to discuss and we can go days and months on this. But now if you want to change the model shape appearance in terms of the vertices, the physical model, right, you change the vertex program. If you want to see how it shades, you change the fragment program, or how it colors. That is why I'm going to go ahead and show you one quick thing, that if I'm supposed to take this triangle, right, and as we saw, I'm going to so to clear this up, I'm going to I have currently applied the color as per the vertex information, right? Now I'm quickly going to change this. Okay, the color is with reference to the vertex in the object space with reference to the pivot. That means I can move it anywhere, the color is not going to change. I can move it anywhere, the color is not going to change, right? Now I want to map it with the color in the world space. All right, now see how this is going to happen. This is going to happen in world space, right? Let me quickly get the shader, select shader, right? Vertex color. Right. I'm not going to show you the code right now, okay? I'm just going to change it if I'm going to do it in world space, all right? You see that the moment I move this in the z-axis, how the color changes. For that, what I'm going to do is I'm going to place the camera a bit far, put the near plane 2.1 and 10. Similarly, if I move it along the x-axis, see, based on the distance of this origin, okay, based on the distance of this origin, I am calculating the position of this vertex, and that data is being provided to the GPU to color it. So what's red and blue? It's pink. What's green and red? See, if I move to 0, 0, 0, this is where it is. If I take it back, this will be, the values are going to be minus, which is 0. So R0, G0, B0, for each vertex, all the colors are 0. And if I just want to make it green, that is how you do it. So it's so simple. On the basis of the vertex position, I'm changing the color of that specific object. And I want you to see how a sphere reacts. Where is the sphere? I'm sorry, guys. This class, this session might go for a bit longer. I'm already suspecting that. I'm sorry. So now if I scale it up, see, even scaling has an effect on it. Why? Because every time I'm coloring every vertex, okay, I'm calculating what is the position of that vertex in the world space. That means if I rotate it here and take it here, you know, and now the deal is, if I say no, I don't want it, I want the color to be with the world position, I want it in the object position, I need to save it. Yeah, now if I move it, it does not change. Did you see that? Because the position of the vertex is with respect to the pivot, and that's why the colors are always going to be based on the distance from the pivot, and that's why this triangle, which has the pivot at the bottom, has more green value than this triangle which has the pivot in the center, because it's going to be the same distance, equidistance. Okay, so I hope you must have understood a little bit. Now let's get on to the practical part of it in a second. I'll just sip some water.
So guys, so far any questions? So what we are looking at here basically is how things are rendered, how whatever the images you see on your game screens are being generated through the code. So shaders are basically the code shading between these vertices. Vertices, how you define the object, the very
Right. So yeah, if you have questions, yeah, please go ahead. That's great. We can have some questions also. Or okay, if you want to go and do a practical, yeah, I'll quickly do a quick practical stuff here. And before we get into practical, in terms of coding a shader, right? What we need to understand is what is a shader, and why is there a specific way to write the shader? Okay. So as we have already discussed, whenever a material is applied to a mesh, the job of a shader is going to compile that mesh and show on the display. right? Which means there should be a specific way for Unity to understand what the developer is writing. That said, okay, that's it. It is an application created by developers itself, right? I should provide, if I am developing a custom application, I should provide.
एक घंटा
Hello.
Rex, can you mute yourself?
Okay, yeah, thank you. So yeah, if I'm writing my own OpenGL application and I want people to modify that application, basically the graphics pipeline, and want them to make it much better, I'm going to provide them an API. What Unity has done is very simple. It has integrated a compiler for CG. Now CG is C for graphics, which is, you know, what happened is Microsoft and NVIDIA, they collaborated to develop a language. Okay. That language is very simple, and the idea of NVIDIA was to, you know, allow the developers to code in one language and then compile the same code either for DirectX or OpenGL. Okay, two major graphic APIs, application programming interface, two major graphic application programming interfaces. So Microsoft said, okay, this CG is great. I'm going to name it as high level shading language, HLSL. And NVIDIA said, all right, perfect, that's perfectly fine. But the syntax is going to be same. That means whenever you write a CG program, you will find that it is very similar to DirectX HLSL shader. And you can always go to the DirectX website and check out their documentation. You won't be puzzled. Okay. OpenGL is a bit different for sure. It uses GLSL. But what is CG? CG, you just write a code in CG, and the CG compiler will ensure that the code is compiled for the right application programming interface, DirectX or OpenGL, which means you don't have to worry whether your application works. Mobile phones, not a problem. Desktops, Windows, not a problem. Species. Macs, not a problem. iPads, whatever mobile devices, not a problem. Gaming consoles, no problem. Xbox, PS, no issues at all. And hence, because it's a language, it should be compiled. But the most important thing that we have to take away from this is it follows a data flow model. That means whenever application hands over the data to the video RAM or the GPU, it is properly placed into specific data structures. And the purpose of this is just going to be take the available data, modify it. That's it. So you have to take the data, modify the data, present it. That's it. No additional writing of data. You can do that, but guys, basics have to be clear. Basic is take the data, modify it. Okay. Then you will go into advanced later. And this is basically a slide that shows how CG basically fits into your application. You write your CG code, okay? You pass the code to CG compiler. If I write my own application, I'm going to connect with the CG compiler, and I'm going to allow my developers to write their own CG programs and let the CG compiler compile offline or at runtime. How does it matter? Okay. If you're compiling at runtime, you can then make changes or modifications to your shader code if it's running. So this is interesting. If you hit the play button, right, and I modify the shader code right here. So if I'm just going to modify the shader code, let's say it just changes. It's compiling at runtime. Nice, nah? So if there's some animation that is running continuously, you can see the animation. You can change the code. It's so cool. That's it. That's it. This is how it fits in this specific environment. And just a quick pointers, because it's a language and it's based on C. There has to be a compiler that compiles the language. This is based on C, so hence C++ things won't be available, like, you know, the object-oriented support, file of input-output operations. Of course, you can include certain files, but you cannot open and read and write certain files, right? It now will provide you CG. CG is going to provide you with a lot of functions. Okay, CG language is going to provide you. If you want, I will definitely share the source of this. NVIDIA's website has a lot of materials. And let me quickly share one page that I'm going to share with you also. Here we go. There is a standard library for CG functions. So see, it is already giving you so many functions. Abs, ABS, absolute. Then we have lots of things, exponential values, derivations. You can just do a lot of things with this. I will share this code. I will share this page with you. Not an issue. No problems at all. And then we need to understand that the best part about this is it executes a relative isolation, which means you can process your vertex data, fragment data, and on multiple threads without any dependency on the previous or other vertices, right? So parallel processing at its best. And of course, if your GPU has some limitations, guys, if you are using a very old GPU, whatever limitations that GPU has, that you will have to face. Okay. Let's dive into the code then. Now we know we have Unity. Unity has objects, they have meshes basically, right? Mesh has a mesh renderer which has a material, that material has a shader, that shader has a CG program. How simple, how interrelated all this is here. It's just a straight flow, right? I'm sorry if I'm sounding too basic, but yeah, this is the straight flow. And let's write a CG program. So whenever you open up a shader file, right, you just create a new, let's say unlit shader. What you're going to see in it is you're going to see this CG program and end CG program, right? End CG. These two keywords are important for the CG compiler to understand. Whatever code you are writing inside of it is going to be compiled by the CG compiler, NVIDIA's CG compiler. Okay, which means that this compiler is responsible to tell the GPU what all mathematical operations and calculations you have to do, or multiplications you have to do, and what all modifications to the data we have to do, right? Now, if you remember the graphics pipeline that I showed you, it had a vertex shader, it has a fragment shader. What NVIDIA did was it provided you a function, right? You have a vertex function, you have a fragment function. So when you start off with writing your CG program, right, you provide a vertex function and you map a vertex function. So basically with the preprocessor directives, I'm saying that this vertex function is basically going to be mapped to simple vertex function. So wherever the simple vertex function is, use this function as your vertex function for this program. Simple fragment function is going to be used as your fragment function for this program. And then you go and compile. I'm not worried about what you compile, how you compile. Compilation is your task. Modification of the data is my task. Simple. Then Unity said that, okay, how do you access the data? All right. So all the data in CG, okay, is stored in structures with no classes, right? Structures, variables, arrays. That is how you store the data. No classes, but data structures are there. So you write a structure. Now, this data, app data structure, is a structure from where you're fetching all the information. Okay. And how you fetch the information is you write a variable. Okay. You're writing a variable called vertex, and you write something called as colon position. These are called as semantics. Okay. How GPU maps your variables to a specific value or type, okay, is called a semantic. That means in this structure I'm defining that GPU, there is a vertex variable that I have defined and I want to map it to the position semantic. So please provide all the vertex data for that specific vertex in this variable. Okay. Once that is done, we are already following the data flow model, which means we are taking the data from the GPU. We are modifying the data in the vertex function. But when you modify this data in the vertex function, right, you need to store the modified data. So where do you store? You make your own structure. Okay, let's follow the basics first. You make your own data structure saying that whatever data I'm going to get from the GPU, okay, which is the positional data for that vertex, I'm going to modify that and keep it in a vertex output structure that I have personally defined so that this data can be passed on to the fragment function. Okay, if I want to pass on this data to the fragment function, I can do that. In the fragment function, if I'm not passing any information from the vertex which is modified, right, I'm just coloring the way I want. It's simple. Because if you remember, where do the object space to world space calculations happen? Vertex function. Because the vertex that we get here is in object space. Why? Because the mesh filter is going to give the vertices in object space. So when the mesh filter gives the position in object space, it is the vertex function's job to convert it into clip space. This data then is used by the fragment function to color up. That's it. In a very simple way, this is a shader. You pick this shader up and put it in a shader code. It will work. But then how does Unity understand? Like if you just give a Unity a file, let's say my shader.txt file, it won't understand, right? So Unity, what it did was it got shader lab in as a mediator, saying that guys, use shader lab, put that code in a specific place, and you know what? It has got some cool commands. So we were like, okay, if Unity wants to understand in a specific way, it's perfectly fine. So what we do is we write a shader file dot shader. Okay, if the shader file is empty, there's no code to compile, right? The shader file should actually start off with a command called shader, and the shader should have a name. Only then will that material recognize that shader. Once that is done, there are a couple of commands, and I'm not going to bore you here, but I'm going to show you by doing this. So somehow Unity just is opening on the second screen. I don't know why. How do you create your shaders? So simple. You create a new folder saying my, okay. I'm shouting, but I'm not shouting. Okay. So ignore that. Create shader. You have so many shaders here, right? Either you create a shader from here and delete all the contents, or you just create a file, name it .shader. So let me do it in a very simple way. I won't do it this way actually, but just to show you. I created a sample.shader file, and now you see it already is considering this as a shader file here. Cool. Now I create a sample material. I'm going to switch off the triangles. I'm going to switch on the sphere. I'm going to reset the sphere so it's somewhere there. I'm going to apply this right here. Now, once I apply the material to this, I just need to select that specific sample shader. So I'm just going to put this here, and boom, it is rendering pink. The problem pink is right up here. Why the problem pink is here is because it's very simple. There is no code to compile. If you check, if you select the material, there is no code to compile. If you select the shader, there is no surface shader, no fixed function, no compiled code, and you have lots of errors. Okay, so now quickly referring to the slide, guys, let's write our first shader. If you want to do that, go ahead, create a shader file, open it up in Visual Studio, double click would do that. Hey, why did it not open up? Or I was too smart to put it somewhere else.
Must
Oh,
be two
sorry.
Visual Studio windows opening. Yeah.
Yeah, it's on the other screen. Sorry. Now let's go as defined in the slide. Okay, so it says it should have commands. So I'm going to move to the next slide. It should have commands. So define your shader like sample shader and a property and a nested this curly braces, right? Not nested but curly braces. Then you go and see. Okay, there is something happening, but there is no shader yet. We have defined a shader. That means your material now identifies this as a sample, right? There is nothing in the shader to compile, but there are certain things that Unity has added because it's a shader, right? It's automatically adding that. Then we know that a shader always has properties. These properties block, as we know, are an interface that is provided by the material. So material, what it will do is it will read the properties and say that, okay, if you have a property that artists can use or developers can use at runtime, I can show it in the GUI. So let's write a property. This is how the properties code block looks like. I'm very much familiar with writing properties. So guys, I'm just going to quickly write a very simple property. It's going to be color. So I will say color A. How do you write a property? So you define the variable, whatever name it is, color A, B, C, whatever, bottle color, glass color, up to you. This is the variable that you define. You give a name to that variable which can be seen in the inspector. So a simple color. I'm going to make it funky. And then you provide the type in the bracket. All right, so the type is, now this you can refer to the document. Unity has beautiful document. You can read all the properties, or feel free, you can connect, not an issue. And then you have to assign a value because you're defining a variable. Without a value, it won't work. So I'm going to say a color as defined by Unity is R, G, B, and A. So let's say R is going to be 0, G 0, B 1, and A I'm going to put it as 1 because alpha. Now here if you write a semicolon, it won't work. The properties block is defined as such that will just require this. And yes, you have a simple color. The color is not compiled. All right, you see a black color. I defined blue, it's black. It's not compiled yet. Why? Because the shader is still pink. Not a problem. We will still go further and code. All right, till the time it's compiling. It's not compiled. So what we do next is, once we have the properties block, okay, we have to write a sub shader. Now what is a sub shader? Basically, if you are writing that specific shader for various devices or platforms and you want to target those specific platforms, you can write multiple sub shaders. Okay, so or even the same platform and different graphic APIs. Okay, you can write a different sub shader. So if you're not using ray tracing, okay, if your graphics card does not support ray tracing, you can write another sub shader and add another code to that specifically works on that specific GPU. So not an issue. But we still have to provide at least one sub shader, right? So we say sub shader, and that is the code block, and we have some sub shader going on here. If we select this, compiled code none, and we have some errors going on, but we'll fix that. Then of course a sub shader, like you see, there are a couple of things. There is a blend command, there's a tags command, there's a LOD, cull, ztest, zwrite, fog, couple of things here and there, and a pass. But now guys, if you must have seen these commands, if we ignore for the moment and see the pass is basically where Unity says that put your CG program right here and I will compile. So let's write a pass. Okay, and it compiles. Why does it compile? It's going back to the default pipeline. Okay, this shader has compiled. You are seeing a basic vertex mapped onto the display, basic model mapped onto the display. The color has automatically turned to blue. That means the compilation is successful. You have a fixed function. Okay, you can see the generated code. This is generated fixed function pipeline. That means it has defaulted to a specific pipeline, and this is the code. Okay, forget it. Let's not confuse ourselves. All right, but this is your first shader that you have successfully written, which outputs a white color. But what about this property? As we have not modified the data, how will GPU understand? Correct? So let's get back to the slide and let's talk about a couple of things that we have not talked about. These commands, right? There are a couple of there's one command that I would specifically like to discuss is tags, where you can define your custom tags also, but where you define that what is going to be your object's render queue. So you don't want to render a glass behind an opaque object. Let's say you're standing in a house, watching outside the window, and there's a tree. You don't want to portray the tree being rendered before the glass, right? So you have a render type and you have a render queue. These two are important things that are important. You have to write in tags so that it is understood by the compiler. Okay, blending will come back to blending, but you don't need to write anything right now. Okay, any of these things you can just quickly skip, because when Unity compiles, it compiles falls back on a specific fixed function pipeline, and you already have an option for the render queue, which is geometry, alpha test, transparent. There is something called as overlay, and then you can increase it to like 6,000 or 6,001. Okay, so Unity will automatically ask you to change your rendering queue even if you don't write that, because that's by default. Even if you don't write a tag, that goes in by default. Now comes the main modification part. So let's put the slide away and keep the Unity and this window open. Let me see if I should do it side by side. That is better. And I'm going to put the console. I need the console. I don't need the hierarchy. I don't need the project. That's it. That's it. So, and console, I'm going to just put it. I'm just going to put it clear. This is the sphere that is being rendered. It is looking like this in perspective in the scene editor mode. Okay, it looks like this in the display. So how do we start writing? As we remember, we have to write our CG program, correct? We have to write a CG program, and in this CG program, we have to take the data and modify it. All right. So we start off with directly CG, and when you do that, just do an NCG. Sit back, boom. It just got to the problematic pink again because there is no CG program to compile. That means we have to start writing a CG program where we have to say that, okay, I'm writing my custom code and I have to give map the vertex and fragment function. So I'm just going to write a preprocessor directive. Assign the vertex function to, what do you want to call it? Simple fragment. Sorted. Now it gives some error saying that there is no fragment function to compile. What are you giving to me here, Videep? I'm a GPU. You're giving me random data. I cannot compile that. What are you doing? So I will say, let's write a function. Now, how do you write a function? Void function name, simple vertex. Any arguments you want to pass? It does not do a KD somehow. It's fine. And then you write a fragment function. Now, guys, you have to understand and follow this step by step, because here there are a couple of things which are defined by the graphic APIs, and you have to be very strict about those. Okay, here you have defined the simple vertex and a simple fragment function, and it's gone. Because first of all, you're not modifying any vertex data. Whatever vertex data is there, it's there, and fragment function is not returning any colors. So let's write, if you want to return a color, what should it be? It should be a float 4. So just like you write vector 3, vector 4, this and that, vector 2, you have to write vector 4 because it's C, and I say return 1. And it goes pink. Okay. Wait, sorry. Yo, where is the shader? Okay, 1 second. 1, 2, 3. Where is the hierarchy? Yeah, here. Project window. Here. So I'm going to select the shader. It says return value is okay. It's got an error, right? So I'm going to go to console. I'm going to just select it. Function return value is missing semantics at line, yeah, 20. So semantics are very important because whenever your fragment is returning a color value, correct? What should the GPU map it to? For now, just understand it should map it to a target. It's a system value command, and you can check the DirectX documents. All right. Awesome. Now your shader is compiled, it's perfectly fine, and it's working fine. But why are you not able to see anything still? Because guys, the data is still not processed in the vertex function. Even if we are providing a simple color to it, we are not providing it a proper vertex function where it's your responsibility by saying that you are defining a CG program. It is your responsibility that you should take the object space positions and the transformations for that specific vertex, do the mathematical calculations, and provide a clip space position or transformations for that specific vertex. Until and unless you do that, how will the fragment shader know which pixels to color? For it, it's not aware which pixels to color, right? So now let's start off with this code. Now till here, I hope you understand. We tried to give a vertex shader, we tried to give a fragment shader, we tried to give output as a color, which is 1. Okay, 1 is basically RGBA1, which is white, but nothing works because we have not modified the data. Now, if you would have seen in the earlier slide, we have to modify the data by taking the data from somewhere, correct? You take the data, you define one structure, okay? In this structure, you say, I want the vertex data. So and this vertex data is basically the position data. So GPU will say, okay, in this structure, I'm going to take the position data and map it to this variable. And then if I have to modify, see, if you have to modify some data in a function, how will you do that? You will take some arguments, correct? What argument? So you have to take type, the argument has to be of type app data, and I can write something as input, but I cannot modify it here and save it here, right? What I'm going to do is I will create one more structure with the same stuff, same exact replica. Okay. I'm going to say this is going to be the output structure from the vertex. So vertex output. Now, whenever you have to write a function that returns a value, what do? Make sure that it returns a value, right? Correct. You make sure it returns a value. So when you have to do that in C, basically CG, you have to first initialize that, right? So this is going to be the V output. And when I say return, you have initialized the structure. Okay, now modify the content. So right now I'm just going to say vertex output, V output has a vert variable, which is going to be the this data structures, input data structures vert. Okay, now guys, you can change it to position. Okay, let's change it to position here, so that you should be aware what you can change and what you cannot, right? And then return, oh I'm sorry, return V. Perfect, you have successfully rendered a sphere, but it's not looking like a sphere. Now guys, one quick question till the time I drink some water. Please tell me why this sphere is not the sphere that we created. Anyone?
We are not doing the the mul function, the vertex multiplication functions based on the camera.
Okay, who's this here?
Avi.
Oh, nice, Avi. Yes, absolutely, absolutely. Sorry for the noise. Okay, 1 second. Right. So here we are not changing the position from the object position to the clip space. So all the transformations that we have to do is not rendering in respect to that frustum. Okay. Now, if we want to do the maths ourselves by multiplying the matrices, we can do that. But Unity has been grateful to provide us a function. Okay. What happens is you have to understand, you have to multiply the model matrix, the vertex, into the cameras matrix, view matrix, into the, that means view projection. When you multiply these three matrices, okay, you finally are transforming that position of the vertex from your mesh filters, meshes, object space to be viewed in camera space. So there is a function, I might have forgotten it, and it's Unity object to clip. This function is provided by Unity. It does object space to clip space by multiplying it by model view matrix, model view projection matrix. Now if I do that, I'm going to get an error. Oh, it worked. Oh yeah, okay, sorry. So this is already available to us. We don't have to. I was actually wondering if we have to include the unity cg.cginc file because that has the common includes, but maybe Unity is already calculating that. So this function is available. Okay, sometimes you write functions and they are not available. Just include the specific include file. And if I'm going to just say that for your reference, okay, this is a multiply function, multiply a and b. A value is going to be I'm going to show it to you on the Unity's website. Okay, 1 second. So there are some built-in shader variables, and there is a, you see, Unity matrix MVP, model view projection matrix, right? So you take this, multiply this matrix with your input dot, what was it, word, right? Now see what happens. Go right here. It's the same. When you get back to the code, it automatically changes. So Unity says that use this function, then you manually multiplying the matrices, use this function. So guys, very much clear, right? Very much clear on what data has to be modified, how the data has to be modified, right? This is your first shader, the very first basic shader. And now we will see how to get this blue color into this function. So what I'm going to do is, because it's a variable, I will go here, I will paste the variable, and yo, we have a problem pink. Because this pass right here, which has a CG program right here, right? It has not defined this variable. What is color A? No one knows. Okay, undeclared identifier. So wherever in the CG program, if you just say this color is basically a float 4, and there you go. Now this is how your artists are going to use your shader. Cool, perfect. Now let's do this. Let's do this. I'm not going to provide this color, okay, but let's try and now get the vertex information into this. Okay, till now we were just writing our custom structures with our custom variables to modify the vertex data so that at least you can see the vertices, right? At least you can see the geometry, right? But now what we are going to do is we are going to make one more variable here. So how do you make a variable? What is the need of the variable? We are going to store the data of this specific vertex in the object space, and based on that data we are going to color. All right, so let me just quickly check how do I get my hierarchy. No, 4. I have my hierarchy here, and in this hierarchy I'm going to switch off the sphere. I'm going to put on the triangle. Why I'm going to put on the triangle is because I want to show you that the same material that we have right now. Where is my custom shader? The sample material I'm going to apply to this. Okay. Yeah. Okay. It's yellow, right? If you go to the inspector, it's yellow. All right. Now what we want to do here is we want to keep a float. Not here. Sorry. We want to take the vertex position in the object space, whatever it is, and we want to modify it and store it in a different variable. Float 4, let's say vertex color. Now the semantics, guys, this is tricky, but guys, please bear with me. Refer to the document from DirectX or buzz us anytime. I know we can use color as a semantic, color 0, and we are mapping color 0 to this variable as the GPU. So the GPU will understand color 0 is V color. All right. And now if I go here, it should ideally not do anything because we have not modified it. So here I'm going to say simply, very simply, that V outputs color A should be, because this is float 4, this is float 4, I'm going to say this is float 4. All right, I'm going to say take the input data, because input data is an object space. I'm going to say take the input data and fill it up with the current object space position. So I do that. Now we have a variable. All right. Sorry, color any ये V color. Guys, बताओ यार. If you find I'm making a mistake, let me know. So vertex output structures, vertex color is being derived from the object space position of that specific object. Okay, so which means for every vertex, the color is going to be the position of that specific vertex in its object space. And then when I say that I need to return this color, all right, here, I have to first take it as an input. So vertex output, I'm going to say it as input here. So typing here, yes. Input dot VCOL. So because the vertex 0 is at green, like 0.5, okay, let me tell you. V0 has X, Y, Z, right? X, Y, Z position. mapped to 0.0 x, 0.5 y, and 0.0. I'm taking this value as x into RGB. All right, I'm mapping this to RGB. So if I was to basically, just to explain this to you, R is going to be dot x dot y dot z, alpha value is going to be 1.0, and I return this. So this is what it is. Now, one more thing, this is sorted. Now this position that I want to, this vertex color, right? This vertex color is the object space, right? That means wherever I move this, sorry, what's fast over here? Fast over here. Wherever I move this, the colors are going to remain the same, right? Now let's get the vertex position in world space. How do you do that? So Unity has provided a function. It's not a function, it's a matrix. It's a matrix, okay? It's a matrix. It's called Unity object to world matrix. You have to multiply this. So I'm going to pull it here so that it's more visible. This matrix has to be multiplied with this input vertex. So we do it similarly. We do multiply object to world with this and save it in the color. Now your vertex is going to have the colors as per the world. So wherever every vertex goes towards the right side in the x direction, right? The R value is going to be, x is going to be more, so R is going to be more. If it goes right up here, x and y, so red and green basically is going to be yellow. X is 0, green, and everything is 0, but I'm going to just move it in the z direction, so blue. So guys, RGB color and position mapping, I hope you're clear. We are just mapping the position XYZ and putting it in the color RGB. That's it, straightforward and simple. Is that fine? All clear? Till here? I hope we are good.
Yeah, that is totally okay. Yeah, we can definitely understand and move ahead.
Awesome. So now guys, it's already 1 hour and 1.5 hours. I'm just going to quickly make you understand one more thing. Let's take a look at how we can modify the positions in this. Because we are already getting the position in this, okay, I'm going to remove the color. I'm going to remove this. We don't need this. I'm going to remove all this code. I would say sorted, and this is an issue with this. So if I just clear up the console, yeah, I'm not reading the mesh now, so it's fine. So we got the color back, right? And reset. So now let's say I want to modify this triangle, right? It's very simple now. How do you modify a triangle? Take the position. Let's say I want to move it. Wait, not here, not here, not here. Very fast. I want to modify it in object space, world space, or clip space. We have to identify that. Now, if you want to modify this in object space, right? Which means first we say float 4 current v vertex position is equal to input dot vert current position dot x plus equals 1.0 1 unit, and we just take this instead of this and place it here, and there's a problem. Current v pose है यार. See, I say I have put an F there. So guys, this is object space vertex transformation done in a shader where you can move it. I'm just going to quickly show you if I'm just going to add a sine wave with respect to time. Okay. So Unity provides a basic variable of time also. It has got floor values. You can see it moving in speed and all. So if you see it right here, is it playing? Okay, so now it's playing, guys. You can see the triangle moving. Now we can take the advantage of the runtime compilation and make it move real fast. Cool. That is your real-time object space transformations. If you want to transform it in the world space, what will you do? Very simple. You will convert this into world space first. All right. So this is going to be input.vertex, but I'm going to multiply it with and here right here is the same. But if you move it, it is going to be multiplied with the world space, right? And if I was to just do it in the object space, it's going to be in the object space itself. Time.w, sorry. All right, so it goes faster. So guys, this is how you modify the information that you are getting. And now let's quickly write that shader that I was showing to you earlier. A very quick and simple shader, and the same concept we are going to use. What we are going to do is we're going to create a plane in the hierarchy. So create 3D object plane. This plane has to be at whatever location you feel like. Okay. Remove the triangle. Assign this sample shader. So watch the plane moving zigzag. Cool. And now guys, what are we doing is perfectly fine, just that we have to do it in the y-axis because we are going to move the shader. So this is perfectly fine. Now your plane is moving up and down and a sine wave value, and this is perfectly fine, right? Sorry. All right. Now what happens if I remove the plus equals? It's just going to multiply it by sine, right? Where is the material? Where is the material? Here. So we have a color and we are applying a color. Now what we want to do is we want to quickly take up a texture and apply a texture to it. So let's say texture, some text. I forgot what it was for texture. Yeah, I mean, I think it's 2D. Yeah, it's 2D. And we have to say like, this is how you declare it, white. And if you go here, if you see the sample, if you see the inspector, you have got a texture and you select a texture. So you select this carpet texture. Exactly the same problem that we faced, right? Exactly the same problem that we faced. What we have not done is we have not taken the texture and sampled it. Now guys, this is going to be a little lengthy again because we have to take the texture and sample it. For textures, what do we need? We need the UV positions. So let's say float to UV. We want to get the UV from the, what do you say, GPU, and this is going to be text code 0. I'm just going to copy this. Sorry, copy paste right here. This is how I'm just going to keep it for the moment. And then here to map the texture, what I'm going to say is our input already has UV. So I forgot the texture. I forgot the value. I mean this thing here. Sorry, I'm so sorry. Transform texture. So we are using transform texture. All right. And what we are going to do is copy. So we're just going to use the transform texture. and it has got two values, right? So if you see here again, I've given two values. We are mapping that specific texture to the UVs. Okay, so the transform text function, don't remember, it's perfectly fine. It is there in the CG documentation. Always refer to the documentation. And sorry, and what you can do is you can just provide the UVs as the first argument and the texture as the second argument. So when you provide the UV, it's going to be input.uv and the texture. Now, how will you get the texture? You can just say texture text. It won't work, right? It will not work because we have not defined it somewhere. So we have to define. How to define it? It's a sampler 2D. It's again a type, data type by NVIDIA. So text, and now here it gives an error. Why it gives an error is because even though we have a text here, we have not provided the tiling and offset information. That is automatically compiled. So how do you provide that? It's of type float4 because we have 4 values, tiling and offset, and just write text underscore st. This is the standard way of defining. It is already predefined. Any text you take, you provide st, and okay, yeah, it is okay. I did not read the error. It says transform text is not defined. Okay, so when it says transform text is not defined, here is where we actually say include a library called CGINC. And guys, any include files that you want to include, in this program have to be of a format called CG include, CGINC short form. So this is already defined by Unity. It's already there by Unity. This Unity file, you can, if you download the built-in shaders, you can get hold of this. This contains a transform text function. And there we go. It's perfectly working fine. Super. Next, what we have to do is we have to return not the color, but we have to map the color. So whatever texture is, we have to map the texture to that specific pixel as per the UVs. So I'm going to write float4 because RGBA is what we're going to return. Color is equal to the mapping function is text 2D. It takes in two parameters. It takes in the texture, so it's going to be text, and the UV. So in UV is going to be input.uv. Now I might be wrong because of this text, how it is defined, but let me just try my luck here. Yeah, so I think it is text 2D. Perfect. So you got your texture here. All right, and you got your texture here. It's moving my direction. It's going perfectly fine. You don't have to worry about that. But this is not what we expected, right? We have to make it move in a wave, right? So to make it move in a wave, we'll come to that. I mean, we just have to offset the specific vertex by that specific vertice's position. So what I'm going to do is sign of time W will be the same for all the vertices, okay? And whenever you draw a sine wave, the Y position is actually the sine of X, right? So I'm going to copy this, delete this. There you go. You have finally plotted a mathematical function in a graphical way. But it does not animate because it does not take into consideration the time, right? So, wow. So this is how it is. Now, if you multiply it, you see what effect you're getting because you're multiplying it by its time. All right. So just go and say add the time to it. Now you see how fine this is. So next, what we are going to do is we're quickly going to take a value to control its speed. All right. So the value is going to be speed value again you have to type your own name. So speed, what is the type? Float. It's not float, it's not flat, it's float. I'm really sorry guys, it's taking a lot of time, but basics I think are taking a lot of time. Whatever the value comes, I'm going to multiply it by the speed. That's sorted. We'll get an error because of course the speed is right here, but it's not defined here. So we're going to find float. Guys, there are other data types called half, fixed and all. Don't do it right now. You can write them. Basically floating is like 32 point precision, and then 32 then there's half is I think 16, and this fixed is 8. I just don't do that right now. It's fine if you don't do it. What is the error? We put I just pasted the line there. So if I increase the speed, okay, I'm multiplying the whole thing by the speed. So guys, the speed has to be multiplied inside with the time variable. All right. So let's increase. Okay. Speed is increasing too much here. Last but not least, we have to add transparency to this. Now, because this texture that I've gotten from the internet, textures.com, okay, let me take the main camera and put it a bit here. Now you see it's getting clipped, right? Now why it's getting clipped is because the camera, it has a property of far plane of only 10. I'm going to increase it to like 50. And in the project, sorry, in the inspector, this camera, I'm just going to basically rotate it like this. So now you see there is some clipping that, some alpha values that we need to put. And how do you put the alpha values? Simple, there is one simple command which says blend. If you go on the unit documentation, this blend command, what it will do is it will take the previous input and blend the current output on that, on top of that. Okay. So we want whatever the previous input is, whatever it is, we want the alpha of that, which is source alpha, whatever the source alpha is. And for this one, in this pass, what we are going to do is we're going to do 1 minus source alpha. Which means it will add the alpha value to this, and there you go. It is perfectly clipped or transparent. So if I go and see this, I'm going to maximize it. This is how it is with the wireframe on. See that? Now guys, I would like you to experiment this with world space object transformations. Write this code, transform this vertex values in world space, and send it across. All right, try that. So I think that is it for this session. We have been able to create our own shader by modifying the vertices in real time using a shader. No animation is required. And this is a programmable function pipeline. We have changed or modified the pipeline on the go. So any questions, guys? Over to you. Avi, over to you actually.
Fantastic, fantastic. It was a complete, very well description of how shader works, how rendering pipeline works, different sort of rendering pipeline like HLSL and CG shaders, how they work. So we wrote a CG program today. We wrote in Shader Lab. Shader Lab is basically UTs, as already Videep explained very well. So any questions, guys? Do you guys have any questions? We are about to wrap up this session. If you have any questions from Videep. Yeah, Lokesh.
Nothing from the question side, but thanks to Videep, it was a pretty beginner friendly session. Thanks a lot.
Fantastic, fantastic. So yeah, we got to know a lot of details about this stuff. So I have one question from Videep. So Videep, so I got to know I was programming with Unity very happily, and I was able to do transformations, rotations, and scale. And pretty much that is the 80% of the what it takes to create a game in Unity. Thanks to the simplicity of Unity. So I got to know about shaders and all that stuff when I started writing shaders. After 2 years, I think in 2015, I started writing shaders. Then I came to know that there is so much to explore. So what was your first reaction when you came across shaders, and how did you figure it out? So would love to know the story for inspiration of everyone who's listening.
Oh, nice. Yeah, actually, yeah, that question takes me back to 2011. Basically,
Yep.
I was a 3D artist earlier, guys.
Hmm.
I learned programming by first starting off with Max script. Though in my school days I used to program on Visual Basic and create Windows applications, but when I got to know about 3D, right, I was so zapped. Basically, like it's amazing how it works.
Yep.
And I used to apply a lot of materials in 3D Studio Max. And I used to wonder, like, how is this done? Yeah, how is this done? How is
Yeah.
it done? I had no clue about graphics at that time. So that was the very first time when I, started exploring how you color, shade, and how these things look so amazing. So that was the very first experience for me to write, get familiar with shaders. And then when I joined my company IOMedia in 2011, uh, and we started using Unity then at that time. Basically, we started in 2013 with Unity,
Yep.
4 point something. That is when my mentor Girish Sarwal, I really salute to him because he started explaining shaders and all. And because of his explanation, it was so simple for me to understand and read shader code that I could go home and do my own experiments.
Fantastic. I think shaders are the best way to explore how computer vision works or how computer graphic works, and you get to know a lot of things. Now we saw example of vertex shaders. With fragment shaders, we can also do all sort of image manipulations. There are compute shaders, and you are exploring everything and putting out the details video about them on your channel. So definitely subscribe Videep's channel, and there you will get a lot of these detailed sessions about how to proceed with shader programming and everything. So thanks, Videep. We are really delighted to host you today, and we got a lot of knowledge about these streams. So Disha, do you want to say something? Yeah, are you asking something? No. Okay, cool. So Videep, thanks for being on the show, and we really enjoyed your session today. And whoever needs a certificate, you can connect with me, you can write me a message. I received a few requests. Those who have already sent me requests for the certificates will receive it tomorrow. And thanks for being on the session and learning with us.
Thank you so much, Avi. Yeah, thank you so much. Even I enjoyed it, like going back to the basics and understanding, telling things basically, and
Absolutely.
making
Yep.
sharing the knowledge.
Definitely, yeah, willing to collab in future as well, and yeah, we can bring a lot of value to the community. Thanks for all your contribution, and yeah, really loved it, really enjoyed it, and it's a great thing to begin with. So thanks everyone for being on this journey, this workshop, and yeah, see you next week.
Thank you. Bye bye. And keep coding, guys.
Yeah, obviously, keep coding. Thanks guys, thanks for being here, and we are pretty much ending the session.